Welcome to the lesson on non-metallic aircraft materials. By the end of this lesson, you will be able to identify the major non-metallic materials used in aircraft and describe how plastics are used in both structural and transparent applications, such as windows and canopies. You will also be able to explain how composite materials are structured, including the role of reinforcement and resin, and how these materials achieve high strength with low weight. You will differentiate between different types of fiber reinforcements and understand how laminated and sandwich structures are designed for performance. In addition, you will analyze the key advantages and limitations of composites. Finally, you will recognize common rubber materials used in aircraft and relate their properties to specific applications. To begin, let us understand how aircraft materials have evolved over time. Early aircraft were primarily constructed using wood and fabric because these materials were lightweight and easy to work with. As technology advanced, aluminum became the dominant material due to its strength and durability. However, in modern aircraft, the use of aluminum has significantly decreased, and non-metallic materials now play a major role. These include plastics, composites, rubber, and sealants, which offer advantages such as reduced weight, corrosion resistance, and improved performance. The cabin image shown here represents how many interior components today are made using non-metallic materials. Wood was widely used in early aircraft structures, especially in wings and fuselage frames. However, its use today is very limited due to issues such as susceptibility to moisture, decay, and lower durability compared to modern materials. Today, wood is mainly found in restored aircraft or some home-built designs. As shown in the image, early aircraft relied heavily on wood structures, but these have largely been replaced by stronger and more reliable materials in modern aviation. Let us examine how plastics are used in aircraft. Plastics are widely used throughout modern aircraft because they are lightweight, corrosion resistant, and easy to shape. They are used in structural components, interior trim, and transparent enclosures such as windows, canopies, and windshields. Plastics allow manufacturers to create complex shapes that will be difficult with metals. In the image, you can see a manufacturing process where plastic components are being formed, highlighting how these materials are shaped for aircraft applications. To better understand plastics, we need to look at their two main types. Aircraft plastics are classified as thermoplastics, and thermosetting plastics based on how they respond to heat. Thermoplastics soften when heated and harden when cooled, which allows them to be reshaped multiple times without changing their chemical structure. In contrast, thermosetting plastics undergo a chemical change during curing and become permanently hard. Once cured, they cannot be reshaped. This distinction is important for maintenance and repair because it determines how the material behaves when exposed to heat. Next, let us focus on transparent plastics used in aircraft. These materials are used in canopies, windshields, and windows, where visibility and strength are critical. Transparent plastics are manufactured in two forms, monolithic and laminated. Monolithic plastics consist of a single solid sheet, while laminated plastics are made by bonding multiple layers together. As shown in the cockpit image, these materials must provide clear visibility while also withstanding pressure, impact, and environmental conditions. Building on that, let us look at laminated plastics and stretched acrylic. Laminated plastics provide improved shatter resistance, which makes them suitable for pressurized aircraft. If damaged, they are less likely to break into dangerous fragments. Stretched acrylic is a specially processed plastic that is stretched before forming, which improves its strength and resistance to cracking. This makes it more durable under impact and stress. Now that we understand these materials, proper handling and storage become critical. Transparent plastics are protected with masking paper to prevent scratches during storage and handling. These materials are easily damaged by scratches and gouges, which can weaken the structure and reduce visibility. Sheets must be stored carefully to avoid bending or unsupported overhang. As shown in the image, proper handling techniques are used to prevent damage. Additionally, plastics should be stored in a cool, dry area away from heat and solvent fumes, with temperatures not exceeding 120 degrees Fahrenheit. Now let's move into composite materials, which are widely used in modern aircraft. A composite is formed by combining two or more different materials to achieve improved properties. In aviation, composites typically consist of reinforcement materials such as fibers, combined with a resin that binds them together. Common examples include fiberglass, carbon fiber, and Kevlar. These materials are widely used because they provide high strength while maintaining low weight. The images shown here illustrate composite layup and manufacturing processes used in aircraft structures. To understand composites further, let us examine their structure. Composite materials consist of reinforcement and resin working together. The reinforcement, which may be fibers, whiskers, or particles, provides most of the strength. The resin surrounds and binds the reinforcement, holding it in place and transferring loads between fibers. This combination creates a material with properties that are not possible with either component alone. The image shown demonstrates how composite materials can be shaped into strong and lightweight structures used in aircraft components. Now that we understand their structure, let us look at the advantages of composites. One of the most important benefits is their high strength-to-weight ratio, which allows aircraft to be lighter without sacrificing strength. Composites also offer high stiffness, good corrosion resistance, and long service life. They provide greater design flexibility, allowing engineers to create complex shapes. In addition, bonded construction reduces the need for fasteners, which can reduce weight and potential failure points. While composites offer many advantages, they also have limitations that must be considered. Inspection of composites can be difficult, especially when detecting internal defects such as delamination. The materials and processing equipment are often expensive, and repairs require specialized knowledge and training. Additionally, some composite materials and chemicals can be hazardous to health. As shown in the image, protective equipment is required when working with composites to prevent exposure to harmful particles and vapors. Next, let us focus on fiber reinforced materials used in composites. Reinforcement provides most of the strength in composite materials. There are three main types: particles, whiskers, and fibers. Particles have equal dimensions, whiskers are extremely strong but less commonly used, and fibers are the most widely used form. Fibers are long, thin, and provide excellent strength when aligned properly. Common examples include fiberglass, carbon fiber, and Kevlar. The image shows layered fiber material, which forms the base structure of many composite components. Let us now understand how these materials are arranged to form usable structures. Composite materials are typically built by stacking layers, which are called laminates. In a solid laminate, multiple layers of fiber and resin are bonded together to form a strong structure. This provides high strength and stiffness, but it also increases weight. To improve efficiency, sandwich structures are used. In this design, two strong outer layers, called face sheets, are separated by a lightweight core such as foam or honeycomb. The core does not carry much load, but it increases thickness, which improves stiffness significantly. As shown in the diagram, this structure allows a component to resist bending loads while keeping the weight low, which is critical in aircraft design. Now, we move on to reinforced plastics, which are widely used in aircraft. Reinforced plastics are thermosetting composites made by combining resin with fiber reinforcement, usually fiberglass. The resin provides shape and bonding, while the fibers provide strength. These materials offer a high strength-to-weight ratio, good corrosion resistance, and excellent electrical insulation properties. Because of these characteristics, reinforced plastics are commonly used in radomes, antenna covers, and wingtips, where structural strength and electromagnetic transparency are required. They can be manufactured as solid laminates for strength or as sandwich structures for weight reduction. The selection depends on the load requirements and the function of the component in the aircraft. Moving from structural materials, let us now look at rubber and its role in aircraft systems. Unlike composites, rubber is not used for structural strength, but for sealing, cushioning, and vibration control. It is essential for preventing leakage of fluids, gases, and air, especially in hydraulic and pneumatic systems. Rubber also absorbs shock and reduces noise, which helps protect components from damage due to vibration. Different types of rubber are used depending on operating conditions such as temperature, pressure, and exposure to fuels or chemicals. Here is a comparison of the common types of rubber and their uses in aircraft applications. Natural rubber provides excellent flexibility and elasticity, but it has poor resistance to fuels and solvents. Because of this limitation, its use in aircraft is restricted, and it is typically used in applications such as water or methanol system seals where fuel exposure is not a concern. Butyl rubber has very low gas permeability, which means it does not allow gases to pass through easily. It also resists weathering and certain hydraulic fluids such as skydraw, making it suitable for hydraulic seals and gas retention applications. Buna-S rubber has good aging and water resistance, but it does not perform well when exposed to fuels or oils. Because of its durability under repeated loading, it is commonly used in aircraft tires and tubes. Buna-N rubber is widely used in aviation because it offers excellent resistance to petroleum-based fuels and oils. This makes it ideal for fuel hoses, tank linings, gaskets, and seals where fluid compatibility is critical. Neoprene rubber provides good resistance to weather, ozone, and oil, making it suitable for external seals, hoses, and flexible components exposed to environmental conditions. Silicone rubber performs well across a wide temperature range, maintaining flexibility at both very high and very low temperatures. It is commonly used in high-temperature sealing applications and for electrical insulation where thermal stability is required. Let us now summarize what we have learned in this lesson. Non-metallic materials are widely used in modern aircraft because they help reduce weight while maintaining strength and performance. Plastics are used in many areas of the aircraft, including structural components and transparent enclosures such as windows and canopies. Composite materials are formed by combining reinforcement and resin to produce strong and lightweight structures. The type of reinforcement and the laminate design directly influence the strength and behavior of these materials. While composites offer many advantages such as high strength and corrosion resistance, they also present challenges related to inspection, cost, and safety. Rubber materials are used in aircraft systems based on their ability to resist temperature changes, fluids, and environmental conditions. Thank you for your attention.